Can someone confirm if you can view, you are able to view the screen?
Yes, ma'am.
Okay, thank you.
Screen is visible.
Okay, thank you. So, hello everyone. Myself Chaitra Borkar, a PhD student from Indian Institute of Technology, Delhi, and I welcome you all to the 10th live session of the NPTEL course, Basic Environmental Engineering and Pollution Abatement. So, let's get started. So some information about these live sessions. So these sessions are conducted every week and they occur on Saturday every week from 3 to 5 p.m. The live sessions link have been shared with you all, and these sessions are recorded and the recordings are made available to you through my YouTube channel. So let's look at the lecture 46 to 50 that were conducted for the week 10. So, in lecture 46, we looked at the industrial pollution control in grossly polluting industries. So, this section of industrial pollution control in GPIs started with looking at the firstly the sugar industry, and now for week 10, we looked at the different industries such as distilleries, tanneries, refineries, copper smelting, and so on. So first, now we discuss for pollution control in a distillery. So what does a distillery do? So it basically utilizes the agro products such as it can be cane juice, it can be sugar beet, it can be sugarcane molasses or coarse grain or wheat, for example, to produce alcoholic beverages. So, if we look at a worldwide from the worldwide perspective, mostly the coarse grains are the majorly used raw products to make alcoholic beverages, as they are used in the distillery. However, in India, molasses are majorly used as the raw material, and the molasses, as we had seen in the sugar industry section, that this is the mother liquor which is produced and contains about 40 to 45% of fermentable sugar. So we had seen after the multiple effect evaporator and the vacuum pan boiling, we get mesic white. And that mesic white, when the crystallization is done, this sugar crystal is separated from the mother liquor, and this mother liquor is called the molasses. So molasses is the raw material for the distilleries which are there in India majorly. And what a distillery does basically, it is the fermentation of molasses to ethanol using yeast, and yeast contains enzymes such as invertase and zymase. So what invertase does is it converts the sugar or the sucrose which is present in the molasses to fructose and glucose, and then this glucose and fructose are converted to ethanol by zymase. And this is a image showing molasses. So now we look at the process flow sheet for a distillery. So here we see that just a minute. So here we see that the sugar mill molasses are weighed and then they are diluted, and then yeast is added for propagation, and then it is took into fermentation tanks, and the fermentation occurs here, and it can take quite a time for the fermentation to occur. Next, it is taken into the clarified wash tank, and through there it is taken into the decanter, where these separation occurs of the sludge from the wash. So sludge is taken as the biomanure, and here wash is taken into the analyzer column. So these are basically distillation columns. So in the analyzer column, the bottoms which are collected are called spent wash, and in the next column, which is the rectification column, the bottoms which are collected are known as spent lees. So the spent wash is taken into the multiple effect evaporator, and from there all separation occurs, and the concentrate and condensate are produced. So the concentrate is taken into the boiler, which is co-generated with bagasse to form the steam, and this steam is actually used to power the rectification and the analyzer column. So we talked about the concentrate. Now the condensate from the multiple effect evaporator goes into the CPU, and the CPU will look at in the next slide. So CPU is the condensate polishing unit. So the permeate from this goes into the UGR, which is a materials or sort, which basically refines the liquid which is present, and it is fed into the fermentation tank again. And the spent lees, which is the bottoms from the rectification column, it goes into the CPU. Also, fuselage is one more sort of a byproduct which is generated from the rectification column, and the refined product, which is the rectified spirit, it is received into a receiver, then storage, and then issued into the vats. And the molecular sieves are also used, and the rectified spirit from the storage tank goes into the molecular sieves, and we get the absolute alcohol then received and then stored. So the few sources of pollution here can be, we can say that it is spent wash or spent lees or the cooling tower blowdown. And if we are cleaning the fermenter, then the water which is generated from that cleaning, that is also a wastewater. So now we look at the condensate polishing unit. So here, as we saw in this slide, that from the MEE, the concentrate and the condensate is forming, and this condensate is going into the CPU. So the condensate here and the spent lees along with the spent lees. So also spent lees as well as the condensate are going into CPU. So they come from the MEE, the condensate comes, and the spent lees from the rectifying column. So they are taken into the equalization tank for this to maintain the consistency of the wastewater, and then into the conditioning tank, and then from there it goes into ICX. This is basically an anaerobic digester. And from there, as we see, the obviously if it is anaerobic digester, biogas will be produced, CO2 and methane. So the gas is generated, and it is uh, taken out through the flare, and the sludge, the wastewater, treated wastewater, is then taken into the aeration tank, and then it from the aeration tank it goes into secondary clarifier, and here we mix the treated wastewater with the cooling tower blowdown, and then it goes into the high rate solid contact clarifier, and from there it goes into multigrade filter, then to the activated carbon filter, then to the ultrafiltration, then RO, and then UV treatment, and then it is again used in the plant. So here we see that basically, firstly, the secondary treatment is done, and then the tertiary treatment is also done. So this is for the recovery of the water, and which can be reused in the plant. Next, we look at the wastewater treatment schemes that are employed in the distillery industry, and for different types of waste, you can use different treatment options. So here we look at the first is the biomethanation, and other is the direct evaporation. So the distillery wastewater can be firstly evaporated, then the sludge which can be generated can be used for incineration, and can also from there you can recover the potassium. And biomethanation can also the refuse from the methanation can also be put into the evaporation tank. Also, it can go for two-stage aerobic treatment, and the wastewater which is generated from here can be gone into irrigation, or it can go for tertiary treatment and then can be discharged into the surface water. So, for the distilleries in India, it is compulsory for zero liquid discharge. So, the treatment of the wastewater should be in such a way that the COD content, the BOD content, or the suspended solid, or the total solids which are there in the wastewater should be minimum as possible, or should be below what is the stipulated limit. Also, the sludge management for the distilleries can be such a way that the sludge generated from the primary treatment and the secondary treatment is basically is basically used for to make biomanure. So the ash which is taken from the boiler. So we saw that the boiler is used to generate steam. So the boiler ash which is generated from there, because it has the boiler uses bagasse and the concentrate from the multiple effect evaporator. So that boiler ash which is generated is has a 12 to 14% about potash content. So this is mixed with the sludge which is generated from the primary and the secondary clarifier, and it can be used as a biomanure. Also, you can there is also a way to make biocompost which can be used as fertilizers. So this was about the sludge management. Also, the air and noise pollution control for the distilleries was also discussed. Next, we look at the industrial pollution control in the tanneries. So, what are tanneries? They basically treat the skin or the hide of animals to produce leather. So, here we see that a person is hanging up these treated leather array or an array of treated leather. So, what tanning does basically, it alters the protein structure of the skin to impart durability. And earlier, a chemical compound called tannin was used, which was taken from the bark of trees. However, now chromium salts are used for the tanning process. So different at different stages in the tannery, you get different grades or different quality of the leather. So it can be either wet blue, which is the most rudimentary form of leather. Then you go, if you refine it more, you get the crust, and the finished leather is the final product which we get. So we now look at the process flow sheet. So this is listing all the processes which are involved in the tannery. And here we look first that the raw hide or skin, it is first soaked into the water, and then from there it goes for liming and unhairing, and from there it goes for flashing and de-liming, because you need to remove the lime, and then from there baiting and degreasing, and then the pickling process, and then from there it goes for chrome tanning. So here the chromium salts are added, and then from this process we get wet blue. So all of these processes are highly water intensive processes. So the water is used in large amounts here, and the wastewater which is generated also has a lot of COD, BOD, and here if you see, it can also have chromium salts in it. And we know chromium is a heavy metal which is a very toxic pollutant. And from here, from the wet blue, when the wet blue is generated, it can go for samming, splitting, shaving, etc. Then rechrome and neutralization, then dyeing and fat liquoring. So fat liquoring is a process which actually imparts uh, it is a process in which oil is introduced into the leather, so that it gives it some tensile strength, some frictional coefficient, some appropriate frictional coefficient is imparted to the leather here. And then from there it goes into drying, and then we get the crust. And the further refining of this crust gives us the finished leather. So the few sources of pollution, as you can see here, is the soaking, because you're soaking it into the water, and a lot of waste can be generated from there. And then liming, because the flesh needs to be of certain it needs to be a bit soft, so that the unhairing or the unhairing can occur. So liming is also a possible source of wastewater. Then fleshing also, then pickling, then chrome tanning, and dyeing and fat liquoring, etc. Next, we look at the treatment scheme for the wastewater which are applied in the tanneries. So there are two types of wastewater streams which are generated, one which can have the chromium and one which doesn't have the chromium. So one which does have the chromium is taken into the equalization tank, and then it goes into the chrome treatment tank, and then from the chrome recovery tank it is again put into the processing unit. However, the other stream from here, the treated water is taken into the primary clarifier, and the non-chromium stream is taken into the equalization tank and collection tank, and from there it goes into the flash mixer. And these two streams, which is the treated chromium uh, treated wastewater from the chromium treatment tank, and the from the non-chrome wastewater stream, they are mixed into this primary clarifier, and from there it is taken into the aeration tank, and from there it goes into the secondary clarifier, and then we get the treated water, and the sludge from here is taken to the sludge drying bed. So here we see the chromium recovery section. So here we see that the from the tanning unit, the chrome bearing wastewater is collected into the equalization tank, and then it goes into the MgO, sorry, chromium treatment tank, and MgO is added here so that it forms chromium hydroxide. And then from here it goes into the chromium recovery tank where H2SO4 is added so that it forms chromium sulfate. And then it goes into the recovered chrome storage tank. So this is how chromium is recovered, and the decanted liquid or the supernated liquid, which is the treated liquid, it goes into the non-chrome wastewater collection tank. So as I said that chromium is potentially toxic, and the sludge disposal for because it can have chromium in higher concentration. So the other routes are not recommended here, such as it can be used as a fertilizer or sorts. Only the landfilling is the suitable option here for the sludge disposal. And moreover, the air and noise pollution abatement for the tanneries was also discussed. And one type of emission, different type of emission which can occur here is the VOCs that can also be emitted. Next, we look at the industrial pollution control for the petroleum refinery and petrochemical industry. So petroleum refineries are those sort of industries where the crude oil is converted into different petroleum products. Here you can see that the crude oil goes for fractional distillation. This is a very rough idea of what the petroleum refinery does. So crude oil goes for the fractional distillation, and you can get petroleum gas, you can get gasoline, you can get diesel, you can get fuel oil, you can get bitumen. So different petroleum products are generated from here. And the petrochemical industry then further converts these petrochemical products into useful chemicals. And these chemicals can be used for making polymers, for making products used in the pharmaceutical industry, for you to be used in the cosmetic industries. So that is the utilization of the products from the petrochemical industry. So now we look at the process flow sheet for a petroleum refinery, and here we see that the entry point is the crude oil which enters the atmospheric distillation unit, and here from here different cuts of the product are there which are taken out from this distillation unit. So here we see the gas is taken out, and after the processing it goes into the Marox treater, and Marox treater is also a source of wastewater, a source of pollution, source of waste which is generating. And the from the gas processing, the fuel gas is taken into the amine treating so that the uh, H2S is removed, and you get the refinery fuel. And further, it is taken into Claus sulfur plant where Claus reaction takes place, and we get the sulfur from here. And the light naphtha is going into the hydrotreater and isomerization plant to give us the gasoline. Next, the same for heavy naphtha. It goes for hydrotreater and the catalytic reforming, and then we get the gasoline. The jet fuel or the kerosene is also generated from here, and it goes for Marox treatment. And diesel oil goes for hydro treatment so that the polluting gases which are there in the diesel can be removed, and we get diesel. the atmospheric gas oil along with the light vacuum gas oil, which is basically the product from the vacuum distillation. It goes into the FCC, which is the fluid catalytic cracking, feed hydro treater, and then it goes into FCC unit. And from there, it is hydro treated. The product is hydro treated and goes into gasoline. So basically, different cuts are further treated so that we can get gasoline. Also, the diesel oil is generated from here, and the jet fuel or the kerosene. Next, the bottoms from here, the vacuum distillation, are taken into the catalyzed coker, and from here the upper cut is taken into the gasoline pool, while the lower pool bottoms from here is the petroleum coke. Moreover, there is a sulfur recovery unit as well. Here, the sour water, which basically has ammonia or sulfur, so it is taken into the this sulfur recovery unit, and steam is passed through this, so that we get H2S, and this is basically a pollutant here. So different pollutants can be generated from the refinery, and which can be spent caustic from the coker unit or the Merox treatment, or the suspended solids or oil, phenols and sulfides. So different types of waste is generated, and these can have different types of pollutants. And the product tree for the petrochemical industry is such that from naphtha, olefins and aromatics are generated, and from there ethylene, propylene, butadiene, benzene, and xylene are generated. And ethylene can be used to make polyethylene. It can be used to make PVC. Polypropylene can be used to make polypropylene or plasticizers and acrylic fibers. And butadiene can be used to make this styrene butadiene rubber or the polybutadiene rubber. And benzene can be used to make a number of a number of chemicals such as cumene or phenol, such as detergent alkylates or malic anhydride, which can further be used to make nylon, polyesters, or detergents. Then xylene can be used to make phthalic anhydride, and these can be further used to make plasticizers. So, a number of products can be found from the petrochemical industries. And the few sources of pollution here can be the volatile organic carbons, because here a lot of organic carbons are being produced. So they can be a source of pollution here, as they can be volatilized very easily. And oil spillage or the leakages, and the process waste emissions. So the treatment scheme for the petroleum refinery is such that, firstly, the primary treatment occurs as the treatment scheme goes, the primary treatment, then the secondary treatment, and the tertiary treatment. So first we look at the bar screens are there, and the oil water separation receiving sound. From here it goes into the bar screens, and through the channel grid and the bar shell flume to the TPI oil separator. So this is tilted plate interceptor. So it basically removes the oil from the wastewater, and from there it goes into the equalization tank, and into the flash mixing tank, and from there it goes into the DAF, which is the dissolved air flotation. So here air is used for the separation of the contaminants here, and from there it goes into bio tower feed sump, and from the bio tower it goes into the aeration tank, and then from the aeration tank it goes into the clarifier, and then from there it goes into so up till here it was secondary treatment, up till here it was the primary treatment, up till the bio tower it was the primary treatment, and up till the clarifier it was the secondary treatment. And after this tertiary treatment occurs, which is PSF, which is pressure swing filters, and ACF is the activated carbon filters, and from there it goes into the guard pond, and from there into the filter backwash, and then and from there it goes into the chlorination compartment, and to the disposal. So for refineries, the sludge management can be as that the sludge is thickened and the cake is transported to secured landfill. So here also the landfills are the recommended form of the sludge disposal. And for air pollution control, so different pollutants can be generated here in the refinery. A lot of pollutants can be generated. It can be H2S, it can be NOx, it can be oxides of sulfur. So different pollutants which are generated. It can also be carbon monoxide. These pollutants which are generated, there is a need to treat that as well. So what one can do for air pollution control here is either they can desulfurize the fuel gas. So the fuel gas which is there, as we saw, there is a Klaus process which is occurring. So you can desulfurize the fuel gas and the sulfur recovery unit. So there is a sour water which has traces of sulfur which can have ammonia as well. So you need to remove the H2S and NH3 from there, and then you can use low NOx burners. The temperature is lower here so that lesser NOx is generated. And then you can use tall stacks for dispersion. If you use lower height of stacks for dispersion, then it will be introduced in the environment where people live very easily. If you use tall stacks, it will be generated at higher altitudes, and it will not come much in contact with the population living nearby. So you can use tall stacks here, and the sour water stripper for the removal of H2S and NH3 is also, as I said, can be used so that there is less of these content in the wastewater which is generated. For lecture 49, we looked at a number of industries in this section. So, firstly, we looked at the pulp and paper industry, then the fertilizer industry, and lastly, the copper smelter industry. So, pulp and paper industry, as the name suggests, it is generating paper from the pulp, which is produced from fibers, and these fibers can be either cotton or cellulose. And most of the pulp is taken from the wood. Nearly half of the pulp which is generated, it is taken from the tree wood. So the process basically involves firstly the debarking and then the mechanical or chemical pulping. Next, the process is bleaching, where chemicals are added to bleach the pulp, which is the most polluting, and then after that washing and then the paper making. So and this is the treatment scheme which is given here. And just a minute. This is the treatment scheme which is given here. And here the wastewater after the primary treatment goes into the aerobic digestion. And from the aerobic digestion, it goes into the aerobic secondary treatment. From aerobic digestion, as you anaerobic digestion, we get the biogas, and from anaerobic digestion goes into aerobic treatment, and from there you get the secondary sludge, which goes to evaporation and then to incineration or landfill. And the water which is generated from here goes into the irrigation or the tertiary treatment. So the as I said that these are these sort of processes which are here, which are involved in the paper making, and all of these processes are highly water intensive. A lot of water is being used here, and the sludge which is generated from these secondary processes or the wastewater treatment processes can be used for agriculture purposes or landfilling. So next, for the fertilizer industry, so fertilizer industry is generating fertilizers such as they can be nitrogenous fertilizers or phosphoric fertilizer or mixed fertilizers which can have nitrogen, phosphorus or potassium as well. So this is the process for the urea production. So here we see that firstly the carbon dioxide and ammonia along with air is taken into the reactor, and this reactor, as I know, is operating at very high pressures and temperatures, and from there urea is formed, and after that it goes into stripping and decomposition. From there it goes into evaporation, and then it goes into prilling, and from there it goes into silos and into bagging. So the stripping and decomposition, from the stripping and decomposition, one stream is going into the recovery and the recycle for the whether the unconverted ammonia or carbon dioxide. So a lot of waste streams are generated here, and it can be in the form of dust. So particulate matter can also be generated here. So dust is generated here, or you can have spillage or leakages. You can have the gases which are being leaking, or which are being purged. So different types of waste are being generated here. So the sources of wastewater can be the process condensate, or the scrubbing tower waste, or the kindly mute yourselves. Excuse me, will you please mute yourself?
Sorry, just a minute. I cannot mute this.
Oh,
There is a problem in my system.
okay, thank you. So, or the cooling water blowdown, tower blowdown, and the wastewater can contain organic compounds, nitrates or alcohols, or ammonia or heavy metals. So this is the one process which I have shown here for urea production. There are different types of fertilizers that can be produced. So in the lectures, it was shown that there were also flow sheets shown for single super phosphates as well as the mixed fertilizer. So I am only discussing here the urea production, but there are other processes which can produce fertilizers, and from there you can get different types of contaminants in the wastewater. And the sources of particulate and gases emission, as I showed here, could be blending or storage or bagging. And the nitrogen removal techniques here can be the steam stripping, or the biological treatment, or the ion exchange. Next, we looked at the copper smelting industry. So, copper smelting is basically the treatment of the copper ores to get a pure form of copper. So, copper ores can be either the oxides or the sulfide form, and the process here is shown here. So, for the sulfide ores, firstly the flotation occurs, and then from there it goes for melting, then the conversion, and then the refining. And for the or for the oxide ores, it can be hydro treatment. It was written as hydro treating there. So basically, it goes for extraction, and then it goes for refining. So different pollution flows can be seen here. So the copper smelting can generate a lot of pollutants such as the VOCs or the dioxins or furans. So dioxins or furans, as was discussed in the lecture 49, was due to the incomplete combustion. So oil on the metal scraps, it basically reacts with the inorganic chlorides, and this forms the dioxins and furans, and a lot of noise pollution can be generated here as well. So now we look at the sample questions related to the assignment 10, and if you and we discuss these questions here so that it will be easier for you to solve the 10th assignment. So first question is, in India, ethanol is mostly produced from. Can anybody give me the answer for this? What is the correct answer here?
Molasses.
Yeah, correct. The correct answer here is molasses, as I had
Molasses.
discussed. Yeah. From the India perspective, molasses are the majorly used raw material, while from the worldwide perspective, it will be the coarse grains. So the correct answer here is molasses. Next question: in sugar industry, multi-effect evaporator is mostly used to concentrate spent wash up to just a minute. I think there is some there can be some confusion here. It better terminology can be used here is distillery basically. Just a minute. It should be distillery. Spent wash is generated in distillery. So in the distillery industry, because both in sugar industry as well as the distillery industry, multiple effect evaporator is used. But the spent wash is generated in distillery. So it will be in the distillery industry, multi-effect evaporator is mostly used to concentrate the spent wash up to dash degree of bricks. So the correct answer here is 58 to 60. So the spent wash before the multiple effect evaporator has about 12 to 13 degree bricks and it is concentrated to 58 to 60 degree bricks. Next question, percentage composition of potash in boiler ash in a distillery is around. So as I discussed, this potash is then the boiler ash is then mixed with the primary and the secondary sludge, and then it is used for biomanure. So this potash content here is about 12 to 14%. Sorry, 14 to 22%. Next question, the physical properties of the leathers are highly improved by so the physical properties can be improved by fat liquoring, as I had said. So the correct answer here is fat liquoring. Next question, in pulp and paper industry, the dash process produces maximum pollution intensity in wastewater. So as I had discussed, in pulp and paper industry, the correct answer here is bleaching. It produces the maximum pollution intensity. So find the most suitable option relating to the component present in wastewaters generated in the chemical fertilizer industry. So can anybody give me the answer here?
Alcohol, ma'am.
No, most suitable option. The wastewater, okay, so I'll give the answer here. The wastewater also have alcohols. Yes, you are correct. It can also have ammonia because ammonia is also used in the fertilizer industry. It can also have cadmium. So all of the above options are correct here. Next question. Identify the suitable option from the following matching different wastewater streams of petroleum refinery and their important contaminants. Description with their final contaminants. So the spent caustic can have what kind of contaminants? It can have the sulfide, the phenols, BOD, COD and oil. So P will be connected with 2. And sanitary waste can have BOD and TSS. So sanitary waste is basically generated because the refinery also have some township around it. So the townships can generate the sanitary waste. So that can have BOD and TSS. So the correct answer here is P2 and Q1. Question 8. Which of the following measures is not appropriate to control air pollution generated in petroleum refinery? Which of the following measures is not appropriate to control air pollution generated in petroleum refinery? So the first option is desulfurization of fuel gas. Second option is installation of sulfur recovery unit or use of low NOx burners or small stacks for dispersion of exhaust gases. You need to find out which of this is not appropriate. So can anybody give me the answer here? what is the not appropriate measure to control the air pollution? Can anybody give me the answer? Okay, so the correct answer here will be we need desulfurization of fuel gas. We also need the installation of sulfur recovery unit and the low NOx burner so that less amount of NOx is generated. And but we need tall stacks. We do not need small stacks for dispersion. So the correct answer here is which is the least appropriate measure to control air pollution. So the small stacks for dispersion of exhaust gases. Next question. The flow rate of wastewater from a tannery industry is 4 kiloliter per day and it has chromium content of 20 milligram per liter. As per CPCB standard, the effluent should not contain total chromium as more than 3 milligram per liter. The rate of chromium removal in gram per day required in ETP. So you are given here the flow rate from the waste flow rate of the wastewater from the tannery industry, and you are given the chromium concentration in it. As per the CPCB standards, you are given that the effluent which is treated should have around 3 milligram per liter of chromium. So how much chromium should be removed? So you are given the incoming concentration and you are given the outgoing concentration. You need to now tell what is the amount which is taken out from this effluent, amount of chromium which is taken out. So this is a rough uh, flow diagram. So this is ETP and this is the wastewater which is coming in. Okay, and this is the treated wastewater. WW means wastewater, and the flow rate here is given 4 kiloliter per day, and the chromium concentration I am taking it as Cr3 plus. So chromium concentration, it doesn't really matter which oxidation state. So the concentration is 2 milligram per liter, and here it should not be more than 3 milligram per liter. So we are taking here as 3 milligram per liter. There's no need for this oxidation state. So Cr here is 3 milligram per liter and here it is 20 milligram per liter. So how much is removed? So we need to find out how much of Cr is removed. So in gram per day. So we know the incoming concentration. We can know the incoming flow. So the incoming flow will be 20 milligram per liter into 4,000 liter per day. So 20 into 4,000 into 2 is 8,000, 80,000 liter get cancelled, so milligram per day. So it will be 80 grams per day. Okay, and the outgoing will be 4,000 into 3. So this has milligram per liter and this is liter per day. So you get milligram per day and this comes out to be 12,000 gram per day. So this is incoming, this is outgoing. So the removed will be in minus out. So that will be 80 minus 12. Oh, sorry, this should be milligram. Just a minute. So this comes out to be 12 gram per day. And 80 minus 12 you get 68 gram per day. So the correct answer here is 68 gram per day. Next question. In an industrial biogas plant, food waste is anaerobically digested to produce biogas. The slurry contains 20% of solid food grains. The elemental composition of the food grains on dry basis is carbon is 50%, hydrogen is 10%, oxygen is 30%, nitrogen is 11%. And this is mass percent basis. Around 80% of the food grains are converted to biogas, and all the converted hydrogen forms methane. If the flow rate of the slurry is 5,000 liter per day, calculate the amount of methane produced. So here the phrasing of the question the is a bit twisted. So here you are given the flow rate here. So flow rate of the slurry is 5,000 liter per day, and the industrial biogas plant food waste in an industrial biogas plant, food waste is anaerobically digested. So the slurry is 5,000 liter per day, and it is anaerobically digested to produce biogas. And the slurry contains 20% of solid food grains. And these 20% of solid food grains has uh, about these percent of CHNO content, and about 80% of the food grains are converted to biogas. So firstly slurry, then food grains. So that slurry has some percent of food grains, and those food grains are CHNO, some content of that is there in the food grains. And some percent of this food grain is being converted. Converted to biogas, which is basically CH4 plus CO2. But here you only need to focus on methane, as we need to calculate the amount of methane produced. So slurry has some amount of food grains, which is 20%, and this 20% of this 20% of slurry, which is food grain, has about 50% or exactly 50% of carbon, 10% of hydrogen, N is 11%, and oxygen is 30%. And these 20% of food grain which has different elemental composition is then converted. And how much of that food grain is converted? 80% is converted. So 80% of the 20% of the slurry, and slurry is 5,000 liter per day. And we are given, so this is basically for, if we go for 1 day operation, 5,000 liter of slurry is being treated, and 5,000, this is volume of the slurry, and we are given the density here, which is 1 kg per liter. So if there is 5,000 liter, so what will be the mass of the slurry? It will be 5,000 kg. So now we'll solve the question here. So for 1 day operation, volume of slurry, it is 5,000 liter, and the mass of slurry, which will be volume into density. So it will be 5,000, as we are given the density of slurry, so which is 1 kg per liter. So we get the mass of slurry as 5,000 kg. So now we are told that there is 20% of food grain which is there in this 5,000 kg of slurry. So the amount of food grain will be 0.2 into 5,000, which is 1,000 kg. Okay, and the amount and this different there this 1,000 kg has different elements which is present in it. So C is 50%. So 0.5 of 1,000. So it is 500 kg. H is 10%. Oh, sorry. 10% will be 100 kg. Next we are given O, which is 30%, and N, which is 11%. So 110 kg, 110 kg. So these are the different amounts of the elements which are present in this food grain. Okay, and next we are told that 80% of these elements are being converted. So 80% of this 1,000, which is 800 kg, or 80% of these each elements are being converted. So converted amount of food grain, sorry, it will be 0.8 into the amount of food grain which is there, 0.8 into 1,000. So 800 kg is the total amount of converted food grain, total amount, okay? And how much will then be, we are told that all of the hydrogen which is converted is producing the methane. So how much is hydrogen being converted? It will be 0.8 into this 100 kg. So 0.8 into 100 gives us 80 kg. Okay, so we are told that 80 kg of H is being converted. And then how much methane will it form? So we know we can write this reaction as C plus 4H gives us CH4, or you can write C plus 2H2 gives CH4, but then you need to account for the amount of H2 which is present here. So we are taking it in an elemental form. So here we write it as C plus 4H, C plus 4H, which gives us CH4. So now we know the molecular mass of these elements here. So this is, if we take it in kilomoles, so 1 kilomole of C, it has 12 kg. 4 kilomoles of hydrogen has 4 kg. CH4 has 16 kg, 1 kilomole of CH4. So if we can make 16 kg of CH4 from 4 kg of hydrogen, then how much can we make from 80 kg of hydrogen? We are given here hydrogen is 80 kg which is being converted. So if we know from 4 kg of hydrogen we get 16 kg. So we apply unitary method here. 4 kg H gives us 16 kg CH4. Okay. So 1 kg of H will give us 16 by 4 kg of CH4. Then how much of CH4 will be made from 80 kg of H? So we multiply it here. So this is 20. So we get the answer as 320 kg of CH4. We can go the other way around as well. So in some questions here you are only asked for methane, but in some questions they also ask how much is CO2 is also being produced. So from here, from this point onward, we can go. We know now the CH4 is being produced is 320 kg. But then how much of C is being used here to produce this CH4? So you can go back as well. So if for 16 kg of CH4, sorry, 16 kg of CH4, you require 12 kg of carbon. So how much for 1 kg of CH4 will you require the carbon? It will be 12 by 16. Okay. And for 320 kg, this one 20 kg. So 240 kg of carbon is being used to make CH4. And you know that 500 kg of carbon is there, but only 80% of that is being converted. So C converted is 0.8 of 500 will be 400 kg. 240 gram of kg of C for CH4. So C for CO2 will be 400 minus 240, which comes out to be 160 kg. And from here you can find out how much of CO2 is being produced using the same unitary method which we use for C to CH4, for hydrogen to CH4. So the correct answer here, as is shown by the solution, is 320 kg. And this 16/4 factor, how this comes out, I told you, using the unitary method. You need to first write down the equation, which is in the elemental form. C plus 4H gives CH4, and then from there you know the molar masses of these elements, and from there you can apply the unitary method to get this factor, so that for how much of kg of H you can produce 80 kg of H you can produce the CH4. So you get the answer here as 320 kg. So is this clear to everyone? This is the final answer you require for this question. Rest is just the extra information that you can use to solve questions in which CO2 is also asked. I hope this is clear to you. And if there are any further questions, you can ask me now. So if there are no questions for this week, I can go ahead and close this session for today.
Thank you, ma'am.
Thank you, ma'am.
Thank you for joining, everyone.
Thank you, ma'am. Thank you.